So let's get started by thinking about what is linear algebra. Well, linear algebra, as the name probably suggests to you, is about algebra on the one hand. And when we think about algebra, we can think about it in a lot of different senses, but in the sense that we're going to think about what algebra is in this course, this means essentially following rules and processes about how to simplify expressions and solve equations. And all the questions that go into understanding how those two things work, and maybe more importantly, when they work. But it's the linear part that gives our course its particular flavor. So that tells us the particular types of expressions and types of equations that we're going to be interested in trying to solve. And so the biggest question for us to sort of wrap our heads around, if we push to the side the question about what is algebra for the moment, is to think about what does it mean to be linear. Now we have a notion from sort of previous understandings that we might have had from previous algebra courses, and also a notion from the author of our textbook about what it is for an equation in particular to be linear. And usually in the renditions that we're familiar with, it looks something like this. An equation is linear in the variables x1 up through xn, if I can write that equation in a way that doesn't use any higher power of the variables than the first power. Notice there's no exponents sitting on x1, x2, etc. And we also haven't multiplied these variables by one another. The only thing that we've done to make this equation, a1x1 plus a2x2 up through anxn equals b, the only thing we've done to those variables is that we've multiplied them by constants, by real numbers, I guess is what we'll say right now, a1, a2, up through an, those are real numbers. And we've added those products together to one another. And that's all we've done. We haven't raised them to powers, we haven't taken square roots, we haven't applied transcendental functions like sines and cosines and logs. The x's don't appear in exponents. The only thing that gets done to them is they get multiplied by scalars, not by one another, but by scalars, single numbers, and then added together. And then the right-hand side of this equation is also just a single number. So that's a pretty practical definition of what it means for an equation to be linear, because that's going to let us pretty quickly spot examples where an equation that we're looking at is not linear. But I want to think, as we're going to do pretty regularly this semester, I want to think a little bit more deeply, and maybe a little bit more geometrically and conceptually, about why this form of an equation is important, why these kinds of equations are going to be the kind we want to study this semester, as opposed to some others. So let's think a little bit more deeply about what it really means for an equation to be linear. So at a first glance, if we think about what the word linear means and where it comes from, the root of that word is the word line. And so where people's understanding of why linear equations are linear tends to come from is first by thinking about what the graphs of those equations look like. So for example, if I only have two variables, and let's say those variables are x and y, then I can write down an equation that takes this type of form, a1x1 plus a2x2, etc., up to anxn is equal to b. I can write down an example of an equation like that in two variables, such as 3x plus 2y is equal to 6. So x and y are my variables. They're being multiplied by constants, so being multiplied by the real numbers 3 and 2. They're being added together, and the result is then set equal to a constant. And if we think about what the set of points in the xy plane that satisfies this equation looks like, that set of points is a straight line when we graph it. Right? If we wanted to, we could solve for y and discover the slope-intercept format. We're actually not going to be that interested about doing that right now. But just to sort of look at the picture and convince ourselves that the word linear is chosen here for a particular reason. And that if I were to change the numbers in front of the x's and the y's and the number on the right-hand side of this equation, then what's going to happen as I change those numbers is I'm going to get probably different lines, maybe different lines with different slopes located at different places in the xy plane. But the point is that all of the equations that I can write down of this form, if I graph them, the result of that graphing is going to be a straight line. So in the two variable case, when my variables are just x and y, and I can visualize these graphs on the xy plane, all of the examples of equations we can write down that take this form are all going to have graphs which look like lines, and that makes them linear. But the hard part about that is this notion of looking like a line. What does that actually mean? That sounds like it's a more geometric question than it is an algebraic question. So let's take a moment to think about ways that we could try to formulate in a precise fashion what it means for a graph in the start of the xy plane to look like a line. And then maybe from that we can extract a new idea of what it means for an equation to be linear that doesn't rely on a visual or a picture or a certain geometry, but can rely on some algebraic criterion that we can test and that we can implement in sort of a conceptual proof-based environment. So what might that look like? The first conceptual shift that I want to make is to start thinking less about the equation itself as being what makes this object here, this line that I've drawn, linear or not. And I want to instead think about those points, those x's and y's, and I call them points because we can look at them in the xy plane, those values of x and y that satisfy this equation. So that's a subtle shift, but we're going to make that shift. Instead of thinking about it's the fact that this equation looks a certain way, we're going to think about the fact that those x's and y's which satisfy this equation behave a certain way. So that's where we're going to start with this. So for example, one ordered pair that satisfies this equation is the point that I can find right here on the graph. Happens to be the y-intercept, although that's not really important for us. But that point is the point 0, 3. And so I'm going to try to be real careful here and write down the following. I'm going to say for x, y equals 0, 3, we know that x and y satisfies the equation that defines this red line. 3x plus 2y equals 6. And so for the moment at least, I'm going to put my focus on 0, 3 and other points like it that solve this equation. What's an example of another point that also happens to solve this equation? Well, let's just be really boring and look at the other intercept. I don't need to use intercepts to do this, but because they give me nice little convenient zeros, it might be kind of handy to do. So we also know that for the point xy equals 2, 0, we know that it satisfies. We know that that x and y satisfies the equation. 3x plus 2y is equal to 6. And so you can imagine that if I had all weekend, I could just go up and down this line and find more and more and more examples of x's and y's that satisfy this, and I could make myself a nice list. That's a list that you might have called a table of values back in an algebra class in high school. But what, of course, the important question is what is it that makes all the values in that list important? What is it that relates them one to another? What is it about the relationship between the x's and y's that's common to all the points on this red line that makes this red line the graph, the sketch of a linear function? So where do we get linear from if we're thinking about tables of values? Well, to do that, let's construct a bigger table of values for this particular function, and then see if we can make some more meaning out of that. So here I've selected some more x values other than 0, 3, and 2, 0. I've selected some other values of x and then used a rearrangement of this equation to find corresponding values for y. So I've labeled 6 points along this line. Technology means that I could list a bunch more points really easily if I wanted to. But again, the question we want to answer is what is it that makes the relationship between all of these different points, both the ones that we've listed and the ones on this line that we haven't listed, what is it that makes that relationship special that's going to let us identify this as a linear equation? And as you might remember from an algebra class when you first were learning about graphing lines, and before you even probably heard y equals mx plus b, what's most important is that the relationship between these x's and y's remains consistent everywhere along this line. I said we wouldn't talk too much about slope, but this is the place where we need to talk about slope. What makes this a linear equation is that if I take any 2 points along this line and I compute the slope of the line segment that joins those 2 points, that answer is always going to be the same regardless of which 2 points along this line that I pick. So we might formulate that as follows. So here's how we're going to put that. We're going to say, for all ordered pairs, x1, y1, and x2, y2, which satisfy this equation, and I'm using the words for all here very specifically because we're about to make a very logically careful point about what we mean. For all x1, y1, and x2, y2 which satisfy this equation, another way to say that geometrically is it's for all 2 points, for all pairs of points that I choose that lie on this red line over here, no matter which ones that I choose, the conclusion is that the value of the slope, and the slope is defined as the ratio of the rise divided by the run. In other words, the difference in the y values of these 2 points divided by the difference in the x values of these 2 points. That when I compute that quantity, regardless of which 2 points that I chose along this line, the answer that I get there should always be the same. So that's what made a linear equation linear back in the y equals mx plus b days. So let's verify that for this particular example before we go on to see what it is that we maybe can generalize out of this. Because one of the hard parts about this formulation is that it's not clear how to use this if we have more than just 2 variables. If we have n variables in our equation, for example, it's not clear how this idea of slope should generalize. But maybe we can come up with something that will allow us to do so. So first, let's just check that conclusion for this particular example. So for example, if I pick the points -3, 7.5, and 5, -4.5. So if I pick this point and that point, and I compute the slope of the segment that joins those 2 points, then the rise, the difference in the y values, -4.5 minus 7.5 is -12. So we go 12 steps down on the graph. The run, 5 minus -3 is +8. So that means I've gone to the right by 8 on this graph. And so the slope can be computed by dividing this rise over that run. And so that slope is -12 over 8. And so the slope between those 2 points happens to be -12/8, which is -3/2. So what if I pick a different pair of points? Let's say I pick 0, 3, and 7, -7.5. Then there, the rise between these 2 points, -7.5 minus 3, that's -10.5. So I'm going down by 10.5 on the graph. And the run, 7 minus 0, is +7. So I'm going to the right by 7. And the slope joining this pair of points is going to be this rise, -10.5, divided by that run, +7. And when I divide the 2 of those out, I also get -3/2. And again, we could continue doing this all weekend by choosing different pairs of points, computing the slope, finding out that we get -3/2 every single time. We could check 100 examples. We could check 1,000 examples. We could write a computer program to check 350 million examples if we wanted to. The problem is that no amount of that work is going to be enough to actually justify to us why this claim, for all x1 and y1, x2 and y2 satisfying this equation, we have a certain conclusion. No amount of work that we can do in our finite lifetimes, or that we can program a computer to do in its finite lifetime, no amount of that work is going to be enough to prove to us that this conclusion is actually true. Because we can't check every infinitely many combination of x's and y's that satisfy this equation one by one in a finite amount of time. So that's not a very good strategy for verifying that this assertion is true or not. Because what we've made here is called a universal claim. This for all that I wrote at the beginning of this assertion is what's called a logical universal quantifier. It means that in order for this statement to be true, it needs to be true no matter which x1, y1, and x2, y2 that satisfy this equation that I choose. Which means, really, that I don't get to choose them at all. I should be able to show if you, or if the universe, were to choose an x1, y1, and an x2, y2 satisfying this equation, then I need to be able to prove that the x1, y1, x2, y2 that you chose has the same slope, right? The value is the same, regardless of which x1, y1, x2, y2 you chose, or the universe chose. Right? And so what we need in order to justify a claim like this is to prove it in its fullness. We need to write down a proof somehow, right, that does not make use of the specific x1, y1, x2, y2 that you chose, or that the universe chose, or that anybody else chose, that somebody handed to me on the street. Right? But we need to be able to write down something, an argument, that will work no matter which x1, y1, x2, y2 that you choose for me. So what might that look like? We're going to wrap up this video by writing a proof of the statement that's over here. And a proof is mathematicians' tool, really our only tool in a sense, for constructing new knowledge and understanding in the discipline of mathematics. If we can prove that something is true, In other words, if we can prove that it logically follows from things that we already assume to be true, that it's logically consistent with those things, then we'll say that we've discovered a new mathematical fact. Right? And to actually discover and to communicate and to write a proof is a craft that mathematicians work on for their entire careers. You might be coming to it fresh this semester. You might already have some experience proving under your belt. But one thing is for sure, that if you're a math major of any stripe, pure mathematician, applied mathematician, industrial mathematician, engineering mathematician, and so forth, chances are proofs are going to be a part of your study for the rest of your mathematical career in one format or another. To some extent or another, pure mathematicians tend to rely a little bit more on proof than maybe other mathematicians do, but really it's not that clean of a distinction. Every working mathematician will be called upon to prove what they know using some flavor of an argument like we're about to make. So let's go through the logical structure of what a proof of statement 2 over here might look like for this equation, 3x plus 2y equals 6. And then we'll hopefully not only learn that we've verified this criterion for the linearity of this equation, but also get our first practice with writing a mathematical proof. So the first thing I focus on when we're trying to prove a statement that has a quantifier in it like this for all, first thing I want to do is focus on my agency as a proof writer. What choices do I get to make as the writer of this proof, and what choices are made for me by the universe, by the reader, by the person who's handed me x1, y1, x2, y2 on the street. And if I can keep those choices straight, then I'll stay out of a lot of trouble in proof writing. So when I see the word for all at the beginning of this statement, that again indicates that I am not choosing, as the author of this proof, values for x1, y1, and x2, y2. Those are chosen for me by the universe. So the first thing I'll do in this proof is to make peace with that fact. And the way that I like to make peace with that fact is by using the word let. So let means that something is about to happen that's out of my control. So let x1, y1 and x2, y2 be chosen. Chosen by whom? Well, not me. They're being chosen by the universe. And so a mathematician will often use a word like arbitrarily. Right? The choice of x1, y1, and x2, y2 is being made not by myself, but by the chaotic forces of the god of mathematics. Let those be chosen arbitrarily, but because we know something else about x1, y1, and x2, y2, we know that they need to satisfy the equation in question. So 3x plus 2y equals 6. So we actually do know something about x1, y1, and we know something about x2, y2. So x1, y1 satisfies this equation, 3x plus 2y equals 6. And therefore, we know that 3x1 plus 2y1 is equal to 6. Right? Similarly for x2 and y2, 3x2 plus 2y2 is equal to 6. So the universe selects for me x1, y1, and x2, y2. We don't get any control over them, but we're going to assume that the universe has chosen them in ways that are going to set up our proof, right? In a way that's going to give me something which satisfies this hypothesis in my proof. x1, y1, x2, y2 need to satisfy the equation in question. And so we at least will know that these two equations both hold for the x1, y1, and x2, y2 that the universe has selected for me. Okay, great. So now that we've made peace with the fact that we don't get to choose x1, y1, x2, y2, but we do get to know something about them, now we can move to the second part of the proof. And in the second part of the proof, we need to justify why this value is the same for all choices of x1, y1, and x2, y2 that we chose. Now, here's a place where we do get some agency as an author of this proof. We need this conclusion to say that this value is the same regardless of the choice that the universe made for x1, y1, x2, y2. But because we did a little bit of work a minute ago, where we verified that not only is this value the same for the two points that we chose, the two pairs of points that we chose on this graph, in particular, that value was -3/2. Notice that this conclusion doesn't require that number to be anything in particular, it just requires it to be the same for any pair of points that was chosen. So for our equation, we can make an educated guess that the value that we're going to get for that slope, regardless of the points that are chosen, is going to be -3/2. So even though we couldn't prove the statement just by checking some specific cases, often checking specific cases can give us an idea of how to make our proof more precise, or how to take the latitude that we're given at the end of this statement, the same, right? It doesn't say what it is, it just says that it's the same. Take that latitude and to use it to actually make a specific choice for that same value. Let's try to show that it's -3/2. So the statement that we then want to prove here is that y2 minus y1 divided by x2 minus x1, the slope that joins the 2 points that the universe has selected, that slope is -3/2, regardless of which 2 points the universe selected, right? And so because we're going to prove that this is always -3/2, regardless of the choices of x1, y1, x2, y2, that will satisfy the conclusion of this statement, that this value needs to be the same, regardless of the choices that were made by the universe for x1, y1, x2, y2. So all we have to do is to prove why this equation holds true, knowing nothing about the values of x1, y1, and x2, y2, other than the fact that x1, y1, x2, y2 satisfy these two equations. And so now is when the plug and chug, the less illuminating part of the proof, but the more technically challenging part of the proof comes in, is we need to figure out how to justify this equation based only on knowing that these two equations are true. So what in the world is that going to look like? Well, anytime we're trying to prove that an equation holds true, the best practice in doing so is following a technique that's called left side equals right side. So often in a lot of British textbooks, it gets sort of written like this. The left-hand side of the equation is equal to y2 minus y1 over x2 minus x1. And our goal, then, is to do a bunch of work, figure out what that work is. It's not going to be too extensive in this example. But ultimately, we want to do some work to simplify that expression iteratively, keep simplifying it and simplifying the simplification and simplifying until, hopefully, we can get it to simplify out to the number that we want, -3/2. And that is the right-hand side of the equation that we're trying to prove. So this is a template for what the rest of our work is going to look like. So we just need to simplify y2 minus y1 over x2 minus x1 far enough until it simplifies down to just the number -3/2. All right, let's see if it works. How could we do that? Well, we have a y2 minus y1 in our equation, but we don't know anything about y2 and y1. We do know something about twice y2 and twice y1. So here's what the author of this proof might do, is to look back at what we know. And that's the two equations that are written right here. So we know that these two equations are true. Look back at those two equations, find the quantities that we might like to simplify, y2 minus y1, and try and get them together in a way that's going to tell me something not just about y1 and y2 individually, but about their difference. So to do that, I'm going to choose here to subtract these two equations. So I'm going to take the second equation, which we know is a true statement. I'm going to take the first equation, which I know is a true statement, and I'm going to subtract the first equation from the second equation. One hopes that in doing so, we're going to get a quantity that we can pull y2 minus y1 out of and use that to help in our proof. So let's see what that looks like. So when I subtract the first equation from the second equation, when I subtract out the right-hand sides, I'm going to get 6 minus 6, which is 0. And looking back at what we know about x1, y1, x2, y2, because they both satisfied an equation that had the same right-hand side, right? They both had to satisfy this same equation. The right-hand sides in a process like this are always going to cancel out and give me 0. So that might be a clue that we can hang on to for later. What happens on the left-hand side? Well, on the left-hand side, my x2 subtracts with my x1, and both have a coefficient of 3 in front of them. So I'm going to skip an algebraic step here, factoring, and just write that as 3 quantity x2 minus x1. Meanwhile, the y's, when I subtract them, same thing is going to happen. 2y2 minus 2y1. That's going to give me 2 times the quantity y2 minus y1. And now take a look at what's happened. By subtracting the first equation from the second, we've now gotten a new equation, which because the original equations were true, this new equation must be true. But what we've won in the process is we've won an equation which now has the quantity y2 minus y1 in it, and that's a quantity of interest in our proof. So my goal now is going to be to get that y2 minus y1 by itself, and then try to substitute that into this expression in an effort to try and simplify it. And you might, if you're clear-sighted, already see where this tactic is going. if I subtract my x's to the right-hand side of this equation, I'll get twice y2 minus y1 equals negative 3, x2 minus x1. And then dividing both sides by 2, we'll get something that hopefully is going to look pretty darn familiar. y2 minus y1 equals negative 3 halves times x2 minus x1. By the way, this might also look a little bit familiar. This is what we might call the point-slope formulation of this particular equation, but we don't need to know that for our proof. What we've done is we've discovered the value of y2 minus y1 in relation to x2 minus x1. And that seems like it's really useful, because now if I substitute that expression for y2 minus y1 into the quantity that I'm trying to simplify in order to finish my proof, let's take a look at what happens. In the numerator, I'm going to get negative 3 halves times x2 minus x1 after my substitution. And then in my denominator, I haven't made any substitution there. I still have just x2 minus x1. But of course, what's going to happen? I have the quantity x2 minus x1 in the denominator as well as in the numerator. And so it's a common factor in this rational expression, which means that as long as it's non-zero, I can cancel that quantity. And what I get, the only thing that survives that cancellation, is the coefficient that's in the numerator that didn't get crossed out, negative 3 halves. And so we've proven, therefore, that even if the values of x1, y1, x2, y2 are selected arbitrarily for me, regardless of what that choice was, I can prove that this ratio, y2 minus y1 over x2 minus x1, comes out to be the same, regardless of the choice that was made. Specifically, it comes out to negative 3 halves. And the only wrinkle that we need to finish ironing out here is that in order to cancel the x2 minus x1s, I had to make that quick assumption along the way that, oh yeah, that needs to be a non-zero quantity in order for us to cancel it out. And we probably should have made that stipulation back here in the original statement, because if x2 were the same as x1, in other words, if this quantity, if this difference were 0, then we wouldn't be able to form this ratio in the first place. So we should probably have also specified for all x1, y1, x2, y2 satisfying the equation for which x1 is different from x2. So I'm going to add that in here. x1 different from x2. Then this conclusion needs to hold, right? So that was just a little thing that I forgot to write down in the original formulation over here. But when we actually sat down to try and write a proof that this equation, the solutions of this equation satisfy this stipulation, we found out that that additional assumption was actually necessary, because without it, we wouldn't have been able to do this last step. We wouldn't have been able to form this ratio in the first place because we would have been dividing by 0. So we need to know that x1 is different from x2. In other words, that we've chosen 2 different points along this line. Otherwise, we can't define the slope in the first place. So that's where we're going to stop this video, but let's take a step back and look at what we just discovered. Okay. We start with the idea that linear equations, which are going to be the subject of linear algebra for us, linear equations are on the one hand about equations in which the variables have only been multiplied by constants, multiplied by scalars, and added together. And the right-hand sides of those equations are just constants. Right? So the linear equations have this particular form. We don't have exponents, we don't have square roots, we don't have other transcendental functions. We only have multiplication of the variables by constants and addition or subtraction of those things together. That's the only operations in our universe. On the other hand, we have this understanding back from Algebra 1, right, which tells us that what it means for a straight line to be straight on a graph is that the slope between any pair of points that we choose is always the same. But that gives us a testable algebraic logical criterion that we can check. And we just went through the process of doing that checking for this particular equation. So we just wrote a proof in which we said for all x1, y1, x2, y2 that the universe chooses which satisfy this equation, so in other words, if the universe chooses x1, y1, x2, y2 such that these 2 equations are each true, then when I form this ratio, which we called the slope in Algebra 1, that ratio will be the same regardless of the choice that was made. And so we proved that by, first of all, understanding that negative 3 halves in this particular example is that same quantity that we're going to be shooting for. And then by using what we knew about x1, y1, x2, y2 to simplify the left-hand side of this equation enough that we can discover that it is indeed equal to the right-hand side. So we've gotten an introduction to what linear algebra is, but we've also gotten an introduction to a proof and how to prove a logical statement that includes the quantifier for all here at the beginning. And that's not nothing. Proof is going to be a main theme for us over the semester, and this is just a taste.